Okay, so as far as the expected value of x is concerned, we've got -2 times 0.2 plus 7 times 0.5 plus 10 times 0.3, and sure enough, that's 6.1. As far as the variance of x is concerned, we got to do the expected value of x squared first. So that's going to be -2 squared times 0.2 plus 7 squared times 0.5 plus 10 squared times 0.3. And that works out to be 55.1. So the variance is 55.1 minus 6.1 squared. And that is 18.09.
Why is it 55.1?
Oh, sorry.
55.3.
55.3. Because whether I'm live or strictly in a room by myself, I still make mistakes. Thank you very much.
He's live.
So obviously there's a tie-in here. Okay. Not just these two cases. We're not just exploring this function for the purpose of getting these two things, but this is how we start the process. So what we've got over here is a specific example of a moment-generating function, specifically the function for this probability mass function. Okay. But to generalize this, the moment-generating function mx of t is the expected value of the function e to the tx, which in the discrete case is the sum over all x of e to the tx times px, p of x. Anytime you're working with an exponential function, you had to worry about this when you were taking integrals of exponential functions in Calc 1. What do you have to worry about with a sum or an integral of an exponential function? What can happen? Think about the graph of an exponential function. What's it do? Okay, we're getting hands again. For those of you not seeing this, we're getting hands over here. What's it look like? What's the graph of an exponential function look like? Yeah, no, okay, so I'm getting hands and getting fingers. Can I get words? It goes to infinity quickly, right? It goes to infinity quickly. Okay. So, and since it goes to infinity quickly, what do you have to worry about when you integrate for an exponential function? That the integral is infinite, right? That you don't have finite area. Okay. So here, if you're doing a summation, you still have to worry about that in some cases. Okay. So what we say here is that mx of t exists if the sum is finite for t less than some value b, where b is greater than 0. Those of you who have had real, when you talked about open balls and closed balls, here we are. Okay. This is probably one of the first places that you actually see some of the classes that you would think never coming together, starting to come together. When you get, for those of you who are thinking graduate school, if you do graduate school in statistics or in probability, you get to an area called measure theory. That's where real analysis and probability meet. You take a look at measure theoretic probability, it looks a heck of a lot more like a real analysis book than a probability book. So,
I hate that analysis.
shh, we're taping. I won't let them know. Okay. So, the reason we didn't have to worry about this for the example that we had is that the value of x that we had in each of the 3 cases was finite. So as long as we have some finite value of t, this whole thing's going to be finite, right? Okay. So, we've got this definition. How in the world does this thing and what we did give us the mean, the expected value of x squared, and so on? So, if we were to write this out, so we talked a little real, now let's pull a little calc 2 in. Okay. E to the tx. Remember this? 1 plus tx plus tx squared over 2 factorial plus tx cubed over 3 factorial, and so on. Remember what that was called in Calc 2?
Is it the Taylor one?
Okay, it's definitely one of the series. It had a specific name.
I don't remember the name.
Okay. Think monster truck rally. 30,000 cubic feet of rubber throwing.
The monster truck series?
Mud thrashing.
The mud series?
Power suit.
Power, power, power. Yes.
What? I didn't get that from the, yeah.
Yes, it is the Power Series expansion.
Mud.
That's what happens when you go to grad school, when you get your graduate degree at an ag school. So, okay, so we're going to make this substitution in here. We've got x times e to the tx, oh, sorry, oops, times 1 plus tx plus tx squared over 2 factorial plus tx cubed over 3 factorial times p of x. So this goes to now, for that specific example, what did we do to get the mean once we had the function written out? What steps did we go through to get that 6.1? took the first derivative and then set t equal to 0. For the expected value of x squared, we took the second derivative and then set t equal to 0. Okay? So keep that in mind in terms of what we're going to do. So if we take a look at the first derivative of this, well, before we get into the process of taking derivatives, what's the one thing that we can do algebraically here? Basic stuff. Asked you these types of questions before and other things. Stuff you didn't need Calc 2 or Calc 3 for. Distribute. Okay, first thing we're going to distribute through is? Yeah, we got to do P of x first. So this is the sum over all x of P of x plus Px P of x plus, actually I'm going to rewrite this second term here. No, I'll leave it that way, never mind. For the, from here on out, for the remaining terms, I'm going to multiply out those numerators, and I'm going to separate out the t's and the denominators, and then leave the x terms with P of x. So this one becomes t squared over 2 factorial times x squared P of x. The next one becomes t cubed over 3 factorial x cubed P of x. And this keeps going on. And all through this, we're operating under the assumption that this is going to be a finite sum, because some of this stuff we can't do without that assumption. Okay. The next thing, the one other thing we can do before the derivative is distributed through the sum. So this is the sum of the x's, the sum over all x of P of x. In each case, what can we pull outside the sum when we distribute it? The t and the coefficient, so this becomes t times the sum over all x of x times P of x plus t squared over 2 factorial times the sum over all x of x squared P of x plus the sum over all x, oh sorry, I left out, let's pull that t, t cubed over 3 factorial times the sum of over all x of x cubed P of x, and this keeps going on.
Should there be a plus sign after the P of x for the first term?
Thank you. It's the sum over all x of x cubed times P of x, and the sum's infinite, so it's plus onward. Got cut off. So, I've got till right about here. So, okay. Here comes the T-ball question of the day. That is 1. Okay. So let's take that first derivative of that with respect to t. What happens to the first term? Gone, right? 0. What about the second term? Remember, we're taking it with respect to t, so what's the derivative of 5t with respect to t? 5. So the derivative is going to be whatever the coefficient of t is. What's the coefficient of t? It's that entire summation, right? Okay. So we've got the sum over all x of x times p of x. Now, for the next term, in terms of the coefficient, well, we're going to bring all of this over, but the derivative of t squared over 2 factorial with respect to t is just t, right? So this term becomes t times the sum over all x of x squared p of x plus this term, derivative of t cubed over 3 factorial becomes t squared over 2 factorial. So t squared over 2 factorial, sum over all x of x cubed times p of x. See what's happening effectively? It's basically just shifting part of it one term, right? So plus, and this is going to go on. So at t equals 0, what happens in this thing? All of these are 0, it's just that, right? Thank you. And that is just the formula for the expected value of x, right? So if you were to take the second derivative, this term's going to drop out, and each one of these summations is going to move another spot to the left. And then when you set t equals 0, the only thing that's going to be here is that part. Okay? So what we get here is ddt of mx of t at t equals 0 is equal to, oh, sorry, dk dtk, I know I was leaving something out, at t equals 0 is going to be the expected value of x to the k. If you need the expected value of x to the 4th, you do the 4th derivative of the moment generating function, set t equal to 0. Probably the biggest mistake that's made along the way is that people go to get the expected value of x squared, and they end up taking the derivative of what you get after substituting in 0 for the first derivative. But that's going to give you a constant, which means the second derivative will work out to be 0. So don't forget, take your second derivative before you set t equal to 0 so that you don't make that mistake. Okay? Okay. So this is where we start with moment generating functions. Now, we went through that long process of getting the mean and the variance for the binomial. That was a lengthy derivation. So if you're looking at, for a binomial, oops. So this is the moment generating function of a binomial, random variable. Mx of t is going to be the sum, okay, for a binomial. What range do we sum over for a binomial? What range of values can the variable take on? Okay, up to the number of trials, but with a minimum of promise, they won't hear it.
I don't have anything to say.
Oh, I thought you said something.
I was like, what the heck?
What you were saying.
No.
Okay.
I didn't even make it.
X goes from 0. Right? We're counting the number of successives. So you can go from a low of 0 to a high of n. It's the expected value of e to the tx. So we'll have e to the tx here times the mass function for a binomial. So we've got n choose x, p to the x, q to the n minus x. Now, just as we did when we were doing mean and variance back then, the goal here is to simplify this somewhat. Hopefully to get rid of the summation. That's basically what we want to do. But as far as this one's concerned, unlike the other situation that we looked at with this, we can't cancel e to the tx with anything else in here. But we can still do some stuff using basic algebra. Okay. If we were going to combine anything in here, what can we put together? Using high school algebra rules. I know, it's been a long time. It's been a lot longer for me, so there. You can combine things if they have the same base. You could also combine things if they have different bases but the same power. So which ones can be combined? E to the tx and p to the x. Okay. Think of e to the tx as e to the t raised to the x. So this becomes n choose x. Put these together, we've got p times e to the t, all raised to the x, times q to the n minus x. So, you say, okay, well, what good did that do us? Well, remember, this is called the binomial distribution because this uses the binomial expansion. This is a binomial expansion. We've got the 0 to n, we've got the two terms raised to x and n minus x, and we've got n choose x. We've got all the things that we need, so this is just equal to what plus what raised to the n. I really need to turn that camera. P times e to the t plus q. Okay. So for any binomial, the moment generating function is going to be equal to this. For the respective values of n and p, you plug those in and get that out. So, I got 2 minutes left. Anybody remember what the formula was for the mean of a binomial? N times p. Okay, so that's what we should get if we take the first derivative and set t equal to 0 for that. Okay, so we want d dt of p e to the t plus q raised to the n. What do we need from Calc 1? Chain rule, right? Okay. N times p to the t plus q raised to the n minus 1 times the derivative of the inside. The derivative of the inside with respect to t is
T,
p e to the t. Okay, so at t equals 0, what happens to that? It's p plus q, which is 1. So all of this is 1, and this piece becomes p. And p. Heck of a lot faster than when we did the other way, right? Okay. So there are a lot of things that moment generating functions are going to be useful for. We'll see some of them in this class before the course is over. What I will do before I pop this video online is I'll go through one more example with a different type of moment generating function so you can see that and have it for your notes. Okay. In the meantime, the other thing that I'll do, since we're not here next Tuesday, is I'll go through the uniform and the normal on the next video. Okay. The uniform, all we're doing is taking the area of a rectangle. That's it. Nice and simple. The normal, you need to make sure you've got your calculator with you because all the calculations are going to be using a pre-built function on your calculator. Okay. The only other thing we're going to be doing is some artwork. Okay. This is bell curve. Okay? So, and just think about this. Same for you guys. Next time we meet, no more political commercials. Okay. Have a good weekend.